Hello and welcome to Gaffy's Grinds. In this video, we are going to do a quick walkthrough of some typical questions that we might find uh, regarding the titration number 5 that we do on Leaving Cert Chemistry course. As you see here, the title is to determine the amount of iron in an iron tablet. This is a very similar titration to the one in titration 4, where we have a reaction between potassium permanganate, a nice purple solution, and a solution of iron 2. In this case, though, the iron 2 comes from iron tablets. So we have to crush up some iron tablets and basically find out how much iron is in each one, or what the percentage of iron is in the tablet. So what's different from the last titration is, in this case, our potassium permanganate is the one we know the concentration of. So in an exam question, they will give you the concentration of the permanganate, which means that we call this our standard solution. And our iron solution we make up with tablets, but we don't know exactly how much iron is in there, so we don't know the concentration. This is what we're trying to do in this experiment. We're trying to standardize it. A little bit of background on iron tablets and why people take them. So I would advise that you just pause the video here and have yourself a little read from there down to there. Okay, so here is some information about iron tablets, why people take them. I'm not going to discuss that. You should have read it yourself. And also in here is explained the reason why we add some sulfuric acid at different stages of the titration. We did this in the previous titration as well, so I won't dwell on it for very long. Again, I advise that you go back and watch titration 4 before you watch this one. All right, so in this titration, we have an oxidizing agent, which is the potassium permanganate. That means it itself is going to be reduced, and a reducing agent, which is iron 2. And again, it is going to be oxidized. We don't need an indicator in this titration for the same reason as the previous titration. KMnO4 is self-indicating. So as the KMnO4 drops into the iron solution, it will decolorize to manganese plus 2. So in the potassium permanganate up here, the purple color is manganese plus 7. And when it hits the iron, while there's still some iron in the flask, they react and manganese gets reduced to iron plus 2, which means that it turns colorless, because manganese plus 2 is colorless. So this continues until there's no iron left in the conical flask, and then the manganese can't be reduced anymore, so it stays purple, and when it hits the flask, it turns the whole solution to pink. So what are we looking for at the end point? Our color change, we're looking for the first permanent pale pink color, exactly the same as our previous titration. Our chemical reaction is also the same. Here is our balanced equation, 1 manganese reacting with 5 irons. So this here is the relationship that we're interested in. All right, some questions regarding this. Some pretty straightforward theory questions from 169 to 173. I'll get you to pause your video and work your way through those now. All right, so which solution is the standard solution? Well, that is the potassium permanganate in this case. Remember that we're working with iron tablets that we don't know how much iron is in, so we definitely can't know the concentration. So we have to know the concentration of the other one, KMnO4. So how do we know that this is the standard solution? Well, we know its concentration. We have to know its concentration. Well done if you got those right. And again, you should only be playing the video if you've had a go at these first. At this stage, we're well into these titrations. This is the 5th one. You have to be getting on top of having a go at these yourself. If you're waiting for me to write stuff down, you're just copying it, 0. You're not going to learn 0, wasting your time doing this. All right, why do people take iron tablets? Again, you should only be watching if you have an answer for this. People take iron tablets to treat anemia. So that's the main reason, to treat anemia, which is a condition where you have low amount of iron in your blood, and then you are lacking what we call hemoglobin, which is a protein in your red blood cells which carries oxygen. So if you don't have enough iron, you can't make enough hemoglobin, and therefore you will always be kind of oxygen deficient. Okay, let's look at the next one. So this is some mistakes that were made in somebody's titration. Jenny crushed up some iron tablets using a pestle and mortar. She left the dry crushed powder to go for lunch. She came back and dissolved the tablets. Explain what's wrong with Jenny's procedure. Okay, well, what's wrong with Jenny's procedure is that she did not add them to acid immediately, and she left them to oxidize in the air. So now the iron 2, Fe2 plus, has now been oxidized to Fe3 plus by the oxygen in the air. To Fe3 plus by the air. And the problem with this is that Fe3 plus does not react with KMnO4. So in our titration, we'll be adding the KMnO4, and we'll be getting a really low titration value because there's no Fe2 to reduce the KMnO4. So we're going to get a very inaccurate titration reading because there's no Fe2 to reduce the KMnO4. So that's a problem. Right, 173. Michael notices during his titration that there's a dirty brown solid forming in his conical flask. What did Michael do wrong? Again, you should definitely have thought about this and you should have an answer. Pause the video if you have not and try and write an answer. Okay, this goes back to us having to add acids for each titration. Remember, we add 2 lots of acid. We add sulfuric acid when we're making our solution with our tablets to avoid oxidation of the iron 2 to iron 3 by oxygen that's dissolved in the water or oxygen in the air. But then prior to each titration, we need to add another batch of sulfuric acid, about 10 mils to the conical flask. That's just here, as you can see, to make sure that there's an excess of acid in the flask. The reason for this is if we don't do this, then the manganese ions, instead of going from +7, they go to, sorry, instead of going from +7, the purple color, to +2, the colorless version of manganese, they go to +4, which is this dirty brown insoluble solid. So what did Michael do wrong here if he's getting this dirty brown insoluble solid? He must have forgot to add the sulfuric acid to the conical flask. Okay, so he forgot to add his 10 centimeters cubed of acid to the flask. Well done if you spotted that as being the problem here. All right, so now we're on to a typical exam question. Like all the other videos about titrations, we've typically included an exam question. All right, so let's see what 174 says. Below is a typical exam question. A student wrote an answer to part C below, but they only got 6 out of 12 marks. Help them to get the rest of the marks by writing out the method and filling in the missing pieces. Okay, so that is this method here. Okay, so at this stage, I'm going to get you to pause the video and we're going to write down the missing bits from the method. So pausing the video and doing this question now. Again, don't just write the gaps, practice writing out the whole thing. What did they do to make up the solution to get the 12 marks? They're missing some key words, so they can't get all the marks. You have to fix this and help them. Pause the video and do that now. Okay, so what we should be saying here is crush tablets using methyl and porter and using dilute. So what do we add to the tablets at this stage? Hopefully what we said is dilute sulfuric acid. We're adding some dilute sulfuric acid to prevent oxidation by the air. Okay, on to the next one. Transfer to a beaker and something the equipment with deionized water. What would that be? Hopefully we said rinse. So we're always wanting to rinse to make sure we're getting all of our iron or all of whatever the chemical is, transferring it all to a volumetric flask. Stir to dissolve, pretty straightforward. Using a something, transfer the solutions and the rinsings to a 250 centimeter cube volumetric flask. Okay, so what would this be? So hopefully you said here using a funnel, transfer the solution to a 250 and that's a volumetric flask. Okay, so you can see why somebody wouldn't get all the marks if they were missing the key names of these pieces of equipment. Drop by drop, add deionized water to the volumetric flask until the something, something, something reaches the something, blah, blah, blah. Okay, so what is the missing here? Well, hopefully you said until the bottom of the meniscus reaches the something at eye level. So hopefully, again, we're talking about the graduation mark, eye level. Stopper and invert, what would this be? Several times. Dilute sulfuric acid, so why do we add the acid up here? What's the reason? Is added to, what's the purpose? So if you didn't know what we had to do here, explain why the sulfuric acid is added. Pause the video, do that now. Okay, so dilute sulfuric acid is added to prevent oxidation of Fe2 plus to Fe3 plus by what would cause that? So again, make sure you've included what would cause this to happen if we didn't add the acid. By oxygen in the air or water. Okay, so those would cause oxidation and then our experiment is not going to work. All right, so you can kind of see why someone would not get all of the marks for what was there before, and hopefully we have improved the answer up to the standard where it would get all 12 marks. Okay, so it's just practicing, going through the steps and making sure we have all the levels of detail we need to get full marks here. Right, now it says complete the calculations in part E. Now this is obviously the hardest bit, okay, but it's not something we need to be worried about, okay? It's something we do need to practice a lot so that it becomes second nature. But, you know, at this stage, you guys should be able to pause the video and go ahead of me and do these. If you're just sitting passively and watching me doing it and copying it down, you're never going to get to the level where you can pre-plan it out and work your way through it. You have to be trying to push on. And this here is just here for you to check your work or for you to find your mistakes along the way. But you have to be brave enough to just pause the video and just go for it at this stage. This is titration 5. We've got 2 left. And if you're not at the stage where you're able to get ahead and do the next bit by yourself, then we're going to have, you know, at this stage, by the time we nearly finish these titrations, you're going to have a problem down the road, because if you can't do them now, it's going to be hard to pick it up later on. So really focus on trying to make sure you can do this now. I've really tried to do it very systematically and show you my process of thinking through these calculations. But we will do it again here. Like I said, you will always be given a balanced equation. And my process for this is always to practice writing out the important parts of the balanced equation. What are the reacting things here? It's these two. It's the iron and the manganese. These are reacting with each other. Okay, so what I'm going to do is we're going to rewrite that down over here. You can skip this step if you like, but then this is probably a reason why you're getting confused and you're getting lost. Okay, I do all this stuff for a reason, because it makes it easier to make sure that you're getting it right. Okay, so it's Fe2 plus MnO4, and the ratio here is 5 Fe2 pluses to 1 MnO4 minus. Okay, now you could skip all this and just start trying to put numbers down and all the rest, but then the problem again is that you're going to get lost, all right, or you're possibly going to get lost. All right, so the next thing I do say is using 2 arrows underneath, classify these materials based on their molarity, their moles, their concentrations, and their volume used in each titration. So we should have a volume in liters and a molarity, or a moles per liter, for each of these. Now, one of them is going to be unknown. Okay, so one of the molarities will be unknown, and that's what we're trying to find. Think about it. What are we trying to find in this titration? Is it the iron we're trying to find, or the manganese? Well, it's iron tablets. We don't know how much iron is in them. So of course, that's what we're going to be trying to find, the concentration of iron. So straight away, that's our question mark. And this is our unknown sample. Now we've got to go to the text and look for the quantities that were used in each titration. Okay, so the information that you need is pretty much all in here in this question. Sometimes it's above that, sometimes it's up here, sometimes it's down here. I think this one is pretty straightforward to pick the numbers out. It's one of the nicer ones I've seen. So let's pause the video and pick the numbers out and put them on the equation. Do that now, please. Okay, so like I said, you should only be playing along if you've done this now. All right, so what have we said? Here, 18.75 cm cubed of a 0.1 molar solution, and all this is talking about potassium permanganate. So we've got everything we need about the potassium permanganate right here. So it's a 0.01 solution, 0.01 molar. And the quantity, of course, it gave it to us in centimeters cubed, but I always say at this stage, convert to liters. So most of us know how to do that at this stage. There are 1,000 centimeters cubed in a liter, so convert from centimeters cubed to liters. Pause the video, do that now. Okay, so the number is 18.75. So what you should have got is 0.01875 liters. Okay, now the next part, it says, was required to react with how much each time of the iron solution. As you can see here, 25 centimeters cubed portions of the iron solution. So each titration had this much. So it's 25 centimeters cubed. So how many liters is that here? Pause the video and write that down. Okay, 0.025 liters. The next thing I would like you to do is I would like you guys to see what the question asks us to do. So it's nicely broken up into 3 separate parts here. There's a part 1, and it says to find the molarity of the iron solution. Find the molarity of the iron solution. So we want to find out what's the moles per liter of the iron solution that we made up. So at this stage, what we want to do is plan out what is our calculation. What should we start with? What should we go to? What should we go to? And what should we finish with? Okay, so I've done this in all the other titrations. So again, my advice to you here is to plan it out first. All right, what do we know and what are we going to? All right, I'll start this off here. Okay, I'm going to give you a chance to pause the video and try and plan out what's the calculation here. Okay, now that I've given you a chance to do that, you should have tried to do it. If you couldn't, I'm going to get started for you. What we know is we know the moles of MnO4 per liter. We know the moles per liter of MnO4. What do we want to go to? Think about the steps we got to go through here. Pause the video and work your way along. Okay, so what we want to go is from moles per liter. Well, we didn't use a liter. We used a certain amount in a titration. So work out how many moles did we use per titration of MnO4. From there, then, we can find out, okay, well, how many moles of Fe did that react with? And then from there, we want to find, well, that's moles of Fe per titration. What's the concentration in moles per liter? So moles of Fe per liter. Now let's go back to the question and show how we've just planned out that. What we wanted to find is the molarity of the Fe solution, moles per liter of the Fe2 plus solution, which is exactly what we will end up with when we get to here. So this will be the answer to part 1. Pause your video now and work your way through that. You've got to get good at planning that through, guys, okay, in your head. All right, so let's go ahead and let's show you how to do this. All right, so I'm going to do this underneath. Moles per liter of MnO4. I'm just picking it out from here. There it is. 0.01 molar means 0.01 moles per liter. Mole of MnO4 per liter. Now you notice how I keep everything labeled. Look at this. I'm doing this for a reason. If you don't do this, you're going to get confused. So don't be lazy. Don't take shortcuts. Do it properly, and then you won't get lost. All right. Then we want to convert to moles of MnO4 per titration. So we need to get rid of the liter. So we're going to times it by a numerator amount of liters, because it's in the denominator here, times it by an amount of liters. Well, what's the amount of liters we use per titration? This number here. So take this moles per liter, times it by 0.01875, and that will give you the moles in that amount. And that's the moles we use per titration. So we're going to go ahead and we're going to get a number of moles of MnO4 now, which is what we were trying to get to here. Moles of MnO4, because that's all that's left here. Moles of MnO4, the liters are cancelled out. So we know we're on the right track. We'll pause the video and work out that problem. Okay, and the number I'm getting here is 1.875, 1.875 by 10 to the minus 3 moles of MnO4. Now I had this done previously, so I'm just going to check that that's still right. 0.01 times by 0.01875, and I'm getting, yeah, 1.875 by 10 to, oh, it's actually 10 to the minus 4. Right? Yes, 10 to the minus 4. All right, and that's moles of MnO4. Okay. All right, so now we're up as far as here. Now what we want to do is find out how many moles of Fe that would have reacted with. Okay, so you go ahead, get ahead of me now, do the next step. Okay, so at this stage, what we want to do is we want to multiply. We want to leave ourselves with moles of Fe as our answer. So we need our answer as a certain amount of moles of Fe. Now at the moment, I've got moles of MnO4, so I need those to cancel. I need to cancel moles of MnO4, so I'll put it in the denominator of this fraction, MnO4. Cancel that, and that means I want moles of Fe on top, so that'll leave me with moles of Fe in my answer. So the next thing I'm going to do is I'm going to go to my equation and I'm going to see what the ratio is. Well, here I can see 5 Fe's for 1 mole of manganese. So 1 mole of manganese on the bottom and 5 moles on the top. Times that by 5, I'm getting 9.375. 9.375 by 10 to the minus 4. Okay. All right, and that's moles of Fe. So now I am as far as here. All right, the next thing I've got to do is get my moles of Fe per liter. So this is moles of Fe, and I need my units to be moles over liters. So what I want to know is, well, how many liters was this the moles in? Well, as I can see, Fe here, and here is my liters of Fe. So 0.025 over here. So I'll put my answer there over 0.025, and I'll get moles of Fe per liter as my answer here. So I'm going to go ahead, stick that in, divide it by 0.025, and I'm getting 0.0375. 0.0375. All right, and that should be my answer up as far as part 1. So that's my moles per liter of Fe, 0.0375. That's my answer, part 1. All right, now let's go and look at part 2. So that should be this done up to here. The next thing I was asked to do was to find the total mass of iron in 250 centimeters cubed. That's what I want to find. The mass of iron in 250. I've currently got as far as moles of Fe per liter. Moles of Fe per liter. So planning out, how would I go from moles of Fe per liter to grams of Fe per 250? Okay, so let's get you guys to pause the video, try and plan out the steps to go from moles of Fe per liter to moles of Fe per 250. Sorry, to grams of Fe per 250. Okay, so you should only be playing along now if you have if you've done this out, if you've planned it out. All right, so currently we have moles of Fe per liter, and we're going to find how many moles there are in 250. Okay, so moles of Fe. So we're going to get rid of liters because we don't want it to be in liters. Okay, so we've got to cancel liters and find out how many moles there are in 250. And then once we have moles of Fe, we want to find out how many grams of Fe that was. Okay, all right, so let's go ahead and do this conversion now. We need to get rid of liters from the denominator because we don't have a full liter. Okay, we're going to go moles of Fe per 0.25 liters. So we're going to times this by 0.25 liters. Okay, and that's going to cancel out our liters and leave us with a certain amount of moles. So we're going to go ahead and do this now. 0.0375 times by 0.25 equals 9.375 by 10 to the minus 3. So this is the amount of moles of Fe I had when I made up my solution of iron. Now I want to convert that to grams of Fe. So I've got moles of Fe and I want to get grams of Fe. Okay, so again, what will I multiply this by so that it leaves me with grams of Fe over here? Okay, so I'm going to need a fraction here. what will be on the fraction. Pause the video and work that out now. All right, well, I need my moles to cancel because there's no moles in my answer. So mole of Fe over here. And I need grams of Fe on the numerator. So moles is gone. For every 1 mole, how many grams of Fe do I have? Go to your periodic table, and I'm pretty sure that number is 56. Which gives us 0.525 grams of Fe. So this is the amount of Fe in 250 cm cubed, or in quarter of a litre. All right, so going back over here now, let's check what it asks us to find the mass of iron in 250 centimeters cubed of solution. So we've got up to here now, okay? So we're almost finished. This is part 2. Done. The last step asks us to find the percentage by mass of iron in the tablets. So let's go back up and find out what was the mass of the tablets. Okay, well look, here it says we used 5 iron tablets. Each of them had a mass of this. So we can do 5 times this to find the total mass of the tablets. Okay, so the last step to find the percentage mass, what we want to do is find the mass of iron in the 5 tablets, which is worked out here. This was the mass of iron in the 250 in the 5 tablets. Mass of iron divided by the mass of the tablets. Now, to turn this into a percentage then, we've got to times it by 100. That's what we do anytime we want a percentage. All right, so what we're going to do at this stage is I'm going to get you guys to pause the video, and I'm going to get you guys to work this out. I'm going to scroll back over so you can see the numbers again for the mass of the iron tablets. And I'm going to get you guys to pause the video and work your way through that now. Okay, so hopefully what we did was we took a mass of iron, which we worked out here. We had 0.525 grams of iron in the 250 cm cubed. And we're dividing that by the mass of the tablets. Remember, we had 5 tablets, and each one of them had a mass of 0.325 grams. So that, by doing that sum there, that will give us the mass of the tablets, all that times 100. Okay, so we're going to pause the video and work your way through that now. And the answer we're getting here is 32.3%. 32.3% is the percentage by mass of iron in the tablets. All right, so that's a pretty typical question about that comes up about the iron tablets, and that's a pretty typical type of calculation. You may be asked to find the grams of iron in 1 tablet, okay, which again, I want you to think about. If you're asked to find the grams of iron in 1 tablet, what would you do here? How would the calculation be slightly different? Pause the video and think your way through that. Try and speak out an answer. What would you do? All right, well, if you're asked to find the mass of iron in 1 tablet, well, of course, this is the mass of iron in the 250 cm cubed, in which there are 5 tablets. So this is the mass of 5 tablets together. So what would we do to get the mass of 1 tablet? Well, we would take this mass and divide it by 5, and that will give you the grams of iron in 1 tablet. That's what we would do there. If that's just how the question can be slightly different in some years. Hopefully, I'm hoping that you guys were able to mostly work your way through that question, okay, and plan it out like I was doing, and plan the next step all the way through. Really important that you can do that. If you can't do that at this stage, I suggest that you go back to the basics, go back to the early titrations and work your way through them slowly, one by one, and see that the first bit is usually always the same. You've got to go from moles per liter of the solution that you know to moles of that solution used per titration, to moles of the other solution, the unknown, and then moles per liter of the unknown. So moles per liter of the thing you know to moles per liter of the thing you don't know. That's the same in almost every titration. And then each titration has a little slightly different bit after that. But you should all be getting the hang of this now. If you're not, you've got to slow it down, go back to basics again. Maybe I'll do another video on just that first bit of each titration and do a few practice examples again, just to remind us of that, because if you don't get that bit, the rest isn't going to come very easy either. All right, guys, I hope you found this video helpful. Again, I know things always seem easier when the teacher is doing them in front of you, but you have to make that transition now by yourselves, going from watching me doing it to you guys doing it and getting it right. You have to make that transition. If you use me as your crutch all the time, then you're never going to move away and be able to do it on your own. So I strongly suggest that you find some other problems, some other questions in your exam papers and start doing them. Titration questions are always question 1. Find titrations that we've done before and do the questions on them. Check the answers on the marking scheme. You've got to keep practicing, power your way through them. Otherwise, if you don't get rid of the crutch, you're never going to be able to walk by yourself, okay? All right, guys, that's it. I will see you in the next video. I will talk about the next titration.